Okay, so first I would like to thank the organizers for organizing this wonderful conference, and I'm grateful that they have asked me to give a talk here. I'm going to be talking about 61,0 theories, and in particular their compactifications. It's going to be based on a work, on this work with Michele Del Zetto and Dan Chi. And a related work has appeared by this group, so there's some overlap with what they have done. And perhaps I should start by saying that the recent developments in the context of studying 60 conformal theories have led to a potential classification of the theories, all theories with 60 superconformal invariants. And this is something that John Heckman will talk in the next talk. So this is a large class that, of course, includes 2,0, the very well studied, even still enigmatic ADE 2,0 theories. But in particular, it also includes a vast number of additional 1,0 theories. And the goal of my talk here is much more modest than what Jonathan will be covering. I will just be taking some examples of these 1,0 theories and study their compactifications. In fact, it's even more modest than that. I will take toroidal compactification on a fixed dimension. So it sounds like it could be totally boring because we're just restricting the class to examples as well as just to a very simple class of compactifications. And the point I want to hopefully convey is that even this is already extremely rich, and I want to convey what kind of lessons do we learn just by doing that. So toroidal compactification of the 2,0 have been more studied, of course. And in fact, we know that the 60 ADE 2,0 theories lead to 4D ADE n equals to 4 supersymmetric Yang-Mills theories. And this actually is nice from the viewpoint of understanding SL2Z symmetry of n equals to 4, as was pointed out by Witten, in terms of a complete theory decoupled from the rest of the gravity modes and all that. So it's a completely field theoretic, so to speak, explanation of the S-duality of 4D theory in geometric terms. And so the natural question to ask is, what about the 1,0 theories going down on T2? What do they give rise to? And do they give rise to theories with SL2Z symmetry? Now, 1,0 has half the supersymmetry, so instead of n equals to 4, we're going to be landing on n equal to 2 theories. And so we can ask, do we get any interesting n equal to 2 theories which enjoy SL2Z symmetries by going from the 60 theory to the 4D theory? In fact, we should first ask the opposite question. Regardless of where they come from, we should ask, are there known 4D n equal to 2 theories which enjoy SL2Z symmetry? And the answer to that is yes. And in fact, in the work of Seiberg-Witten, there was already a beautiful example. SU2 gauge theory with 4 fundamentals already gave rise to a theory with SL2Z symmetry. And this class was extended to other examples. For example, if you take SUN gauge theory quiver on an affine quiver, so quivers which form a ring with bifundamental matter between them, gives you a moduli space, which is a moduli space of point on T2. Again, SL2Z of that T2 will be manifest in this class of examples. And similar classes were discovered for studying SUN quiver theories with very specific ranks proportional to the Dynkin indices, where the formation of the quiver is based on affine D and E quivers. In those cases, one finds that the moduli space of these theories are given by moduli space of flat D and E connections on T2, generalizing this case, which can be formulated as moduli space of flat SUN connections on T2. So one question would be, can we actually explain these SL2Z symmetries from the 60 perspective as the T2 coming from the 60 compactification on T2? Well, what can we do on a T2? It's kind of boring. We just take T2 and it's a flat. Everything is flat. Well, the only thing you can consider doing is turning on Wilson lines for gauge groups or global symmetries, or that's all you can do. So there's very little you can do. And so the question is, can you tune these to get interesting 4D IR fixed points? That's the question we want to understand. So the only non-trivial piece is what are the choices and what can you do, and what do you end up in 4D? Well, in fact, it turns out that there are many 4D theories we can end up with a given 6D theory. You start with one 6D theory, and what we're going to see is that you get many inequivalent 4D infrared fixed points, which a priori have nothing to do with each other in 4D, but they have a common parent in 6D. And we could ask a general question about what do we want to keep in 4D. Well, one thing we could do is say we want to preserve global symmetries, in which case we would not be turning on Wilson line in the global flavor symmetry direction if we want to preserve all of them. So that's one thing we can do. Or we could insist that we want to get a 4D theory for which SL2Z duality is a manifest in terms of this moduli space of the resulting 4D theory as a marginal deformation of the theory. So we could ask these theories. And it turns out that these two generally are incompatible with each other. If we insist on preserving global symmetries, we will not have any manifest SL2Z symmetry, relevant SL2Z symmetry left over. And if we insist on this, we will break some of this global symmetry. That's the thing I would like to show. And the basic strategy is the following. So we want to have these 6D theories. As Jonathan will mention, these theories can be geometrically engineered as F theory on elliptic Calabi threefolds. We then compactify them on a circle, which leads to M theory on the same manifold. So that's in 5D now. So going from 6 to 5. We go one more dimension down to 4, another circle, so that this gives us a torus. So that gives you 2A on X again. And then we use mirror symmetry, which leads to type 2B on mirror geometry Y, where Y is a mirror to X. And the vacuum geometry of the n equal to 2 theory emerges from the mirror geometry Y. So that's the strategy. So in this case, we can then identify what 4D theory we have ended up with. We start as examples with the simplest type of example, what I call A-type, where we can also use brain techniques, for example, Al-Hanani and Zafarani and similar techniques. You can proceed that way to more complex example where mirror symmetry techniques lead to the emergent n equal to vacuum geometry. So I'll start with the easier cases where the brain techniques are sufficient to see the basic picture. So let me start with a simple class of 6D 1,0 theories. As Jonathan will mention, these theories can be viewed as quiver type theories, where these quiver literally are spheres in the base of the elliptic threefold. And you have put some 7 branes wrapping around them, giving rise to gauge groups, in this case SUNs. So you have a theory which have a linear ring of these, linear quiver of these SUNs with some flavor symmetries at the two ends, with suitable bifundamental matter. The conformal fixed point of the 1,0 is reached when all the spheres shrink to a point. So this at the origin, which is strongly interacting, you get this. So I'm describing here just the Coulomb branch where you're deforming away from the conformal fixed points, you get such a quiver description. And it has an SUN times SUN global symmetry coming from these two ends. So now, again, F theory you can realize in terms of branes, or you can realize in terms of F theory on elliptic Calabi threefold. And you can then compactify it on a circle and ask, what is this elliptic threefold? And this has been studied. And it turns out the elliptic threefold is given by an elliptic 3-manifold in this form. So this is a toric description of the threefold, where these lines denote various cycles shrinking in the toric geometry. And the vertical directions are identified. So these double red lines denote that you should think about this as a circle. So you get some kind of a toric realization of the elliptic threefold in this form. And the ellipticity is related to the fact that there's this circle here. And the size of this is given by related to this 1 over r, the radius of the circle that you're compactifying to 5D. You can also view this as in the brain picture as a web of PQ5 branes in type 2B, where, for example, you can think about the horizontal lines as D5 branes and the vertical lines as NS5 branes. So so you put this on a plane with a periodic direction. The plane is cylindrical. So you have a periodic direction with the size 1 over r. So that's the brain construction of these theories. This is in 5D now. So you can see the manifest SUNs when you bring these on top of each other. When the D5 branes come on top of each other, you get the SUN factors here. And then the left and the right give you the global symmetries. And so the only new piece is the fact that there is this periodic direction, which is related to the KK modes that you're ending up with. So now, the most obvious way of going down in one more dimension is just to preserve the global symmetries on the structure that we had in 6D, namely bring them together and think about it that way. You will get a picture which looks like this. You take this 1/r, the fiber size, since r goes to 0, this direction goes to infinity, so the cylinder unwraps itself. And the D5 brane by T duality becomes the D4 brane, ending on NS5 branes. So you get a 4D description with the same quiver, identical quiver, with these SUN gauge factors with bifundamentals between them. So this is the most obvious 4D theory you'll end up with, which preserves the SUN times SUN global symmetry, and nothing fancy has happened. So basically, you take the 6D quiver and view it from the 4D point of view, and nothing has changed. And that's the theory you'll end up with. This is the most obvious one, which preserves global symmetry. But notice that this elliptic fiber direction has disappeared. That is, the SL2Z has no role to play in this theory. This theory is a conformal theory. It's a nice fixed point and so on, but it does not have the natural SL2Z structure we had already put along this direction. So this, you can view it as a genus 0 class S theory of A type with two full punctures. These are the two ends, and then with some simple punctures in the middle, depending on how many gauge groups do we have. But there are other limits. So instead of, if you want to keep this piece relevant, which is where the torus will be showing up, it is natural to take a different limit where you bring them together. And when you bring them together, this is actually, and it's natural to perform an S duality in the type 2B language and view these, for example, as D5 branes, and then an S5 branes this way. And then take another limit where you separate these NS5 branes along the other direction. And now you have a very simple description. D5 branes here and NS5 branes here, but now you have periodic D5 branes cut by these NS5 branes. And now if you go down 1 dimensions, D5 branes become D4 branes. And you just get exactly the theory that we had studied in the context of toroidal 1. You get this ring now, where the M now will be different, will be depending on how many of these factors we have. So you get a different 4D, but now there's a manifest SL2Z symmetry coming from the torus that you're interested in. However, the moduli space, the SL2Z is manifest, but there's no global symmetry anymore. The SUN times SUN global symmetry that we started with is gone in this description. And what happened was, instead, they are reflected by the fact that the moduli space of this theory is a moduli space of SUN connections on T2. So in other words, we interpret this in the following way. The global symmetry, first of all, is broken to a diagonal SUN in the SUN times SUN. And we turn on flat SUN Wilson lines, which was this movement of these branes that I was showing to you, which gives you the position of these NS5 branes. And that is a dual description. So we have broken the global symmetry, but they are not gone totally. Namely, they are showing up in the moduli space of the 4D theory as moduli space of flat connections. However, that's not the end of the story. In fact, you can have a plethora of many different kinds of limits that would be interesting. For example, you can take this limit. In other words, start with these and bring these lines pairwise near each other and separate these guys pairwise. You get a picture like this. And so the 5D version, so this is the picture that you will get in 5D. And if you consider the 4D version of these theories, it's known that these guys are parents of these class S theories, where the number of these lines corresponds to which SUN we are dealing with, which N factor, which A-type theory we are dealing with. So as you can see, you have these two double lines, but you can see the outlines of a Riemann surface here. So indeed, the Riemann surface will have these periodic cycle direction and these other ones cutting through. So we'll have a picture like this. So in fact, class S theory of the A1 type. A1 type is because we had two lines. And of course, I could have a different one. For example, I could have brought three lines together. I would have had the class S theory of A2 type. Here I'm just illustrating one particular version of them. So in this case, you just get class S theory of A1 type with 6 full punctures on a genus 7 curve. So the single theory in 6D is leading up to different, very different theories in 4D with different, so some of them have SL2Z symmetry, some of them have higher symmetries, and SL2Z is only embedded as a part of the modular group in this picture. In fact, we can also study a little string version of these theories in 6D, and the little string version turns out to be in the brain language the same thing, except the left and the right torus is getting identified. So the cylinder is replaced by a torus. And again, you can separate them, let's say like, and now you get a Riemann surface with no punctures. So you get the class A1 theory on a genus 9 without punctures. So the theory you get, depending on which limits you put in, can be a whole host of different possible theories, which apparently in 4D have no connection whatsoever with one another. Even though we can get arbitrary genus class S theories with different types of AN and so on from these class of theories, there is actually, I'm not claiming we land on arbitrary moduli of these 4D theories. As you can see, the shape here is very rigid, the very specific moduli you land on. So in fact, this leads to a purely theoretic notion of swampland. Namely, you could ask, I start with a 4D supersymmetric theory with n equal to 2. Can I get it from a 6D complete theory? And if I can, which submoduli of it may I land with? Do I get the most general one or some subset of it? And so this is, in this case, this suggests that you're only landing on some specific submoduli of the 4D theory in this case. So I don't have too much time, so I'm going to speed up. So now we turn to more interesting, more non-trivial examples in the sense that it's harder to see them in terms of brain picture, but the same kind of story works. So we start with so usually when we talk about type 2B with the orbifold geometry, if the orbifold gamma is a subgroup of SU2, then we know we get a 2-0 ADE theory depending on which gamma we choose. But in the context of F theory, this gamma does not have to be SU2, it could be a subgroup of U2. And for that to be compatible with supersymmetry, we need the non-trivial elliptic fibration. So in fact, you can show that all the 6D theories of F theory are exactly of this type. Namely, they will have, in the 6D base, will have an orbifold-like structure. But I will look at the even more specific structure of them, where the elliptic threefold is itself a fully orbifold story. In other words, this does not say that tau itself is an orbifold, but a subset of them involves the elliptic part, which itself is also an orbifold. So I will study a subclass of these theories, which the geometry is just T2 times C2 mod gamma, where gamma is some discrete subgroup of now SU3, which should preserve the supersymmetry acting on this. Of course, if gamma is a symmetry, the T2 part of it can only be very specific, Z2, Z3, Z4, or Z6. You cannot get an arbitrary one depending on what shape of T2 you choose. So let's simple example. You take a group generated by Zk and Znk, where I'm denoting the first factor is how it's acting on T2, and the other two is how it's acting on C2. So if you take Zk to be one of the case roots of unity, which is 2, 3, or 4, or 6, for which the torus has that symmetry, and you are compensated by something in the visible base of the F theory, so that it's a SU3 holonomy. You take this generator and you take the Znk to be a generator of this type, which is purely in the base of F theory. Then it turns out that this is equivalent in the M theory setup to n M5 brains probing the D4, E6, E7, or E8 conformal D6, D4, E6, E7, or E8 singularities. To see this, consider the case n equals to 1. So let me just take a simple case where n is 1. So you have Zk times Zk generating this group, where Zk is just 2, 3, 4, or 6. In this case, what you find is that each one of them, you get Zk factors, but as was shown by Sen, Dasgupta, and Mukhi, depending on which orbifold you choose for the torus, you get different gate symmetries, which in this case will be singularity locus of some symmetry of the 7 brane. So you get Ek type singularity. Since you have two generators, you get two Ek singularities intersecting at a point at the origin of C2. This turns out to be dual in the M theory language to an M5 brane probing the Ek singularity, where Ek here denotes D4, E6, E7, and E8. But this is what I already discussed partly in the last strings meeting. It's what we call conformal matter. And if you do the n-fold version of this, it corresponds to n points if you replace zk by znk, it gives you n M5 brane probing the AK singularity. So this corresponds to n conformal matters of the corresponding type. So for example, in the base of the F theory, you'll get pictures like this. We get a generalized quiver type theory with SO8 matter, and the matter between them is itself a conformal theory. And similar to E6, E7, and E8, which I'm not showing. And again, they have a very complicated tensor branch. You know, these SU2, E7, etc. come out. So out of these simple orbifolds, Z2, Z3, etc., you get a complicated looking tensor branch with these funny gauge groups with amazing patterns. But anyhow, so you can study all these, and they have self-intersection numbers, which I won't get into details, which are very relevant for studying the 6D theory. But my main point is now compactifying them down to 4D and seeing what we get. Well, we can write down the mirror geometry. You get the mirror geometry, which is like this, with 3 C variables and 2 C star variables. You study them, and you find that there are two particular limits you can get. In one limit, you get n M5 branes that you had gets related to ND4 branes and ND3 branes when you go down successively, probing ADE singularities. But that is the familiar ND3 branes probing AD and E singularities, which will give you these kinds of quiver theories in 4D, which was known, in fact, to have SL2Z symmetry with a marginalized space of flat D and E connections. The case of if you take the case n equals to 1, in this case, you get SU2 with 4 fundamentals. So that case corresponds to the original SU2 with 4 fundamentals for which the SL2Z arises, namely from an M5 brane probing the D4 singularity. That already gives you the SU2 with 4 fundamentals. And there's another possibility where instead you preserve the G times G symmetry, and then this leads to, again, a genus 0 class S theory of E type now, with 2 full punctures and simple punctures like this, similar to what we had in the A type. Since I don't have too much time, I'm just flashing here in terms of what the mirror geometry looks like. So the way the mirror geometry shows the class S theory is that you have a locus of E singularity on a curve, but it will have some punctures. The singularity type changes near some specific points. You can study how they change and identify the nature of the punctures. And you see it's a full puncture or simple punctures, depending on what is the nature of the singularity. So that's how you can read off what's going on there. But just as in the A case, we can tune the parameters differently and get different 4D theories. For example, if you go to choosing the parameters in the mirror geometry, which corresponds to turning on these Wilson lines on the torus, you can arrange it to look like this. And then from that theory, you can get a class S theory of SO8 type, for example, on a hyperelliptic curve with genus n-1 with 4 plus 2n punctures. This is similar to the game I played in the A case, where you can get different higher genus case with different types of class S theories and so forth. In fact, there are other n equal to supersymmetric models which are known or expected to have SL2Z symmetry. And these are related to certain theories that are generalization of D-type Argyris-Douglas introduced by Ceccotti Del Zotto and also Chi, which involves an integer P and a group G. If the group G is SU2, these theories, conformal systems, enjoy G as a global symmetry and P is an integer. So when G is SU2, this gives you the Argyris-Douglas D-type theories, where P labels which Argyris-Douglas you're talking about. But these generalize that to a huge class for any ADE you can take, for example, of this type. And you can check by counting their beta function that if you take 4 of these D2 theories with the G type for any G, or 3D3 or this combinations, and then gauge the corresponding global symmetry for all of them, then you will get a conformal theory. You expect the beta function vanishes. And it's natural to ask if these theories also have exact SL2Z symmetries, and they do have. And they do arise from 60 theories, which are generated by a group ZK and gamma G, where ZK is what I had told you before, and well, slightly different version, this version, and gamma is the gamma of ADE. So this class generalizes the 4, E6, E7, and E8 quiver theories. We can use this on mirror symmetry to solve for the vacuum geometry of these theories. These theories kind of generalize the ADE kind of affine ADE quiver theories I talked about to gauging. So the middle node is the middle node of the D and E affine theories is the G that we are gauging. And the edges that emanate from that are the corresponding matter systems that are DPGs. And so we are gauging them. So this generalizes the affine D and E quivers. And the mirror geometry for them will give you a Landau-Ginzburg theory with 6 variables. So they're not even a Calabi-Yau threefold, but there's a mirror symmetry, gives you a mirror geometry, and you can compute the exact 4D n equal 2 geometry in terms of periods of the Landau-Ginzburg theory, not in terms of a Calabi-Yau, but still, this is effective to compute the result of the 4D vacuum geometry. So just as a last remark, if you take the case of SU2, which is the usual Argyris-Douglas theory, with D-type, with this number 2 and 3 and 4 and 6, etc., you get what the class of theories which are called complete n equal to 2 theories, which correspond to theories in 6D which have only one tensor branch of the type O minus 4, O minus 6, O minus 8, and O minus 12, which lead to these, which have these gauge groups SO8, E6, E7, and E8. So let me conclude. So toroidal compactification of 6D10 theories leads to insights about 4D n equal to 2 theories. Distinct 4D n equal to 2 theories can arise from a single 6D theory. SL2Z symmetry of these 4D theories, some of them can be realized and explained geometrically by the 6D and 6D existence of a 6D1,0 theory. And of course, it would be interesting to study more examples of this class, as well as compactification of these theories on curves to obtain n equals to 1 in 4D, and even circle compactification in 5D should be studied more, or higher dimensional curve geometries to 3 and 2 dimension should also be interesting to study. Thank you.
Thank you very much. Are there questions or comments? Edward?
So in the cases you mentioned where you arrive at a class S theory, but not at generic points on its moduli space,
Yes?
is there a low energy explanation of why the moduli are constrained?
I do not have a, that's why I call it swampland. It's not easy to find the easy explanation. You can just see what you land on. I do not have a direct field theory explanation. So mirror symmetry tells you this is the class you're ending up with. It's clear that let me explain why we expect that that's going to be the case. For example, the SL2Z is going to act, we only have one SL2Z. So if you have these higher genus ones, you have to have a diagonal SL2Z acting on them at the same time. So the curves have the same geometry of the tau. They have the same taus, this higher genus. That already shows that there's some restrictions on what class you're ending up with.
Further questions?
Is there a geometric description of the Higgs branch of all of these theories?
You mean the 4D language or 6D language? They should exist. Yes, in 6D they exist, and I'm not sure, maybe Jonathan will talk, but you can do this but I will concentrate more on Coulomb branch side, on tensor branch and Coulomb branch, but yes, there is.
Other questions? Comments?
I have two questions. First, as a follow-up on what you said before, when you have a restriction on the modular space, do you land on exactly the same 4D theory that you find in class S, which has such an exactly marginal deformation?
Which has such a what?
In sometimes you land on the subspace.
Yes, yes.
Space of some class
Yes.
S theories.
Yes.
So my question is it exactly the same class S theory, which we know has an exactly marginal
Yes. No, you get the same class S theory, except that some of the moduli do not arise, do not have a 6D completion.
No, but that's a property of the four-dimensional theory.
Yeah, so you have, but the point is that these high-dimensional operators they're very specific operators that the 6D theory giving you. So I'm just saying you take a particular limit to get infrared fixed points of these. So you have a very specific structure of what are these irrelevant things that you get rid of, which allow you to have a 6D theory out there. So it's a very specific completion of these theories.
The 4D theory that you landed on has some exactly marginal
Yes,
deformation.
which may not have a 6D completion. That's exactly what I'm saying. So you can move away from this locus, because as you say, 4D theory does have these extra moduli, but there is no guarantee that they have a 6D completion.
The other question is something I didn't understand. You said that sometimes you compactify on T2 and there is no SL2Z. Did you say that?
What I said is SL2Z is irrelevant. That is, they won't show up as any aspect of the 4D theory. So for example, the quiver theory, you will have SL2Z, but the KK modes decouple, so it doesn't act on your theory. They just act trivially on your theory. That's what I mean.
So the theory
SL2Z cannot be broken, of course. It just acts trivially.
The theory you find does not depend on. Is it true that the 4D theory that you find is independent of tau?
Is independent of what?
So
Is independent of tau. The IR theory is independent of tau.
Okay, one last question, Joe.
Yeah.
Okay, so then let's thank Cumran again.